Year 13, Lesson 3, Geometric Sequences and Series. So we're going to start off by reminding ourselves of what a geometric sequence actually is. You have come across these at GCSE as well, and geometric sequences are sometimes also called geometric progressions. So let's write down some simple examples. So 2, 6, 18, 54. That's an example of a geometric sequence. And 8, 4, 2, 1, a half. That's another example of a geometric sequence. Can you spot the connection between the terms and how you progress from term to term? Well, hopefully you can see in the first geometric progression that you multiply by 3 each time. In the second one, you can see that you multiply by half. You could describe it as dividing by 2 to create the next term each time. So a geometric sequence or a geometric progression is a sequence in which each term is generated by multiplying the previous term by a fixed value. Now, this fixed value, which in the first example is 3 and in the second example is a half, is called the common ratio. So let's write down some of the notation that we need to make sure we use. So the first term in the sequence is called A, as it was previously. The number of terms is referred to as n. And again, you might have an infinite geometric sequence or you might have a finite geometric sequence. Now, the common ratio is defined by the letter R. And again, we might refer to a general term as AK. So we're talking in this example about the kth term. So as we did for the arithmetic progressions, we're going to look at finding a formula that will allow us to identify the general term of any geometric progression, provided we're given information about that geometric progression. So let's see how a geometric progression is formed. So the first term, of course, we've defined as A. Now the second term, A2, is created by taking A1 and multiplying it by R, which gives us AR. The third term, A3, again, generated by multiplying the previous term by R. Now, if you take AR and multiply it by R, we get AR squared. So, similarly, A4 will be AR cubed, and so on. And from here, you should be able to see very clearly the pattern is such that AK, which is a general term, is AR to the power of K minus 1. Okay, so look very carefully at the pattern here. And this gives us a very useful result which will allow us to find the general formula for any GP. So let's take a look at the examples that we had previously. So we had the geometric progression 2, 6, 18, 54. Now we can see that the first term A equals 2. The common ratio R is equal to 3, so we can say that AK is equal to 2 multiplied by 3 to the power of K minus 1. And that's as simple as we can write it. Now, does it work? Well, let's have a look at substituting a value into this. So if K is equal to 2, this gives us AK equals 2 multiplied by 3 to the power of 2 take away 1, which is 1, which gives us 6, which is indeed the second term. So we can see that the formula does check out with our little check here. So what about the second example we had? We had 8, 4, 2, 1, a half. In this geometric progression, the first term is 8, so A equals 8. The common ratio is a half, and so AK is equal to 8 multiplied by a half to the power of K minus 1. Now this example is interesting because 8 is a power of 2 and a half is a power of 2. So we can rewrite each part of this. I'm going to write 8 as 2 cubed. And I'm going to rewrite a half as 2 to the negative 1, which is then being raised to a power of k minus 1. So I can now simplify this a little bit further. So this is 2 cubed multiplied by, and remember, if we're working out an index raised to a power, we multiply the indices together. So this becomes 2 to the power of 1 subtract k. And then, of course, we can add our indices, which gives us 2 to the power of 4 minus k. Now, let's check that, as we did last time. I'm going to check it with k equals 4. Now, if you recall, that should give me the fourth term in the sequence, which is 1. So let's substitute that into our formula. So ak is 2 to the power of 4 minus k, or 4 minus 4, which is 2 to the power of 0, which is 1. So this checks out again. Let's see whether we can apply this information that we have now just found. So a geometric sequence has a first term of 2, so straight away a equals 2, a common ratio of 5, r equals 5. One of the terms in the sequence is 31,250. What's the position of this term? So we know that AK equals 31,250, and our job is to try and find K. Well, let's use the formula that we have just found, that AK is equal to A multiplied by R to the power of K minus 1, and that equals 31,250. Well, we can substitute in A is 2, R is 5, and we have this result here. And we've then got to solve this equation to find our value of k. So of course, let's divide by 2 first of all, which gives us 5 to the power of k minus 1 equals, so this equals 15,625. Now, we need to solve this equation here. We're going to solve it using logs. So I'm going to use just log to the base 10 to begin with as an example. So I can say log of 5 to the k minus 1 equals log of 15,625. Now, using my log rule here, let's pull the k minus 1 in front as a multiple. So k minus 1 multiplied by log 5 equals log of 15,625. We then, of course, need to divide by log 5, which will give us k minus 1 equals log 15,625 over log 5, and then simply add 1 to find our value of k. And from here, we can work out that k is equal to 7. Now, having recently looked at the natural log function, we could also solve this equation using ln. I could say that ln of 5 to the k minus 1 equals ln of 15,625. So k minus 1 ln of 5 equals ln 15,625. K minus 1 equals ln 15,625 over ln 5. And then if you work this out on your calculator, you will find out again that k is equal to 7. Now, some of you will be wondering why, when looking at this equation, did I not just use log to the base 5 to solve it? I could, in theory, have written down that k minus 1 equals log to the base 5 of 15,625 and worked out the answer that way. And you're absolutely right, I could have done that. And as you will find, I get an answer of k equals 7 again. So all three methods work. Now, the reason that I would advocate using this method here, log to the base 10, or this method here, ln, is that later on, when you come to solve problems which involve inequalities and logarithmic equations, if you try and use the specific base that the question is set in, so for example like this, you may find that in a situation involving an inequality, i.e. a question involving a less than or equal to or a greater than or equal to or a less than or greater than, you may find you get the wrong answer. Whereas if you use log to the base 10 or ln, you will get the correct answer, providing you do all the steps correctly. So there is sometimes a little bit of a warning required if you're using log to a specific base, which is why, as I've said several times, I would advocate using log to the base 10 or ln when you're solving these problems. So, moving on from simple geometric sequences or progressions to a geometric series. Now, a geometric series is created when you add together the terms of a geometric progression. So, for example, a geometric progression or sequence would be 2, 4, 8, 16, 32. We're just writing down the terms of that sequence. But a geometric series would involve adding these terms together, so 2 plus 4 plus 8 plus 16 plus 32, etc. Now, as we've done with arithmetic series, our aim is to find a formula which allows us to find the sum of n terms of a geometric sequence. So, we're going to go straight into a generalisation here, so please make sure you pay attention very carefully. I'm going to start off by writing out the terms of my geometric progression. So my first term is a, my second term is ar, my next term is ar squared, and then I have ar cubed, and so on and so forth. And my last term, if I have n terms in this geometric progression, will be ar to the power of n minus 1. And the term before that would be ar to the n minus 2. And the term before that would be ar to the n minus 3. Now, that's just a list of terms, so it's a sequence or a progression. If I want to create the sum or the series, I need to add together these terms. So let's write that in. So a plus ar squared plus ar cubed plus all of the terms in this series added together like so. Now, I'm going to write down what would happen if I multiply every term in this series by r. So we're going to multiply all terms by r, the common ratio. Now, on the left-hand side, that is going to give me r multiplied by the sum. On the right-hand side, well, let's have a look at what's going to happen to each of the terms. So a is going to become ar. ar will become ar squared. ar squared will become ar cubed. So each term has a power of r that is 1 higher than it was previously. Let's fill these in. And the last term becomes ar to the power of n. When you multiply by r, remember you're adding the powers together each time. So we have a new summation. Let's put the plus signs in so we can see what happens here. Now, here's what we're going to do. I'm going to call the first result result 1, and the second result, the red and blue one, result 2. I am going to work out 1 take away 2, and we'll see what that gives me. So that is s take away r multiplied by s on the left-hand side. And on the right-hand side, think about what's going to happen. This is going to match with this and subtract. This is going to match with this and subtract. This is going to match with this and subtract. So what's going to happen is all of the terms that I'm shading in green right now are going to cancel when you do a subtraction. So this will cancel with something in the previous list. This will cancel with something in the list below. These two will cancel. These two will cancel. You will be left with the only terms that have no match, which is this one here and this one here. So on the right-hand side, we will have a take away ar to the power n. Now, let's tidy this up. On the left-hand side, I'm going to factorise an s, which leaves me with 1 minus r in the bracket here. On the right-hand side, let's factorise a, so 1 minus r to the power n. And I can rearrange this to give me a formula for s, which is the sum of n terms of a geometric progression. And this is equal to a, bracket, 1 minus r to the n over 1 minus r. And this is an extremely important result, which will allow you to find the sum of n terms of any geometric progression. Now, sometimes people like to write it slightly differently by multiplying both the numerator and denominator of this fraction by -1, which would give you this result here. So the signs in the numerator and the denominator just switch around like that. So you may see this version as well. So let's see if we can apply this to a simple example. So I'm going to pick a geometric sequence. Let's choose the one we had previously, 8, 4, 2, 1 and a half. And I'm going to create a finite geometric sequence here. So my a value is 8, the first term is 8, my common ratio r is equal to a half, and my n value, the number of terms, is equal to 5. So according to my formula, s is equal to a, 1 minus r to the n over 1 minus r. So let's substitute in our values. 8, 1 minus a half to the power of 5, all over 1 minus a half. Input that into your calculator, and this gives me an answer of 15.5. Now, you can check this by adding together 8, 4, 2, 1 and a half, and you will see very quickly as you do this that the answer is also 15.5. So there's a small verification that this works, even though we have actually proven it with our derivation of the previous slide. So we're now going to look at a few very simple examples involving this formula. Let's read through the first one. So a geometric sequence has a first term equal to 2, and a common ratio of 5. Find the sum of the first 8 terms of this sequence. So s is equal to a, 1 minus r to the n over 1 minus r. Let's substitute in our values. 2, 1 minus 5 to the power of 8 over 1 minus 5. Substitute that into your calculator, and you get an answer of 195,312. Let's look at a second example. So we have a finite geometric sequence with n terms, a first term of 3, and a common ratio of 2, and the sum of these n terms is 98,301. So find the number of terms n. So we know that this number of terms adds up to a total of 98,301. What is the number of terms? So let's make use of our formula here, and we know that a is equal to 3, so we have 3, bracket, 1 minus 2 to the power of n over 1 minus 2, which equals 98,301. So simplifying this, we can work out that 1 minus 2 to the power of n is equal to negative 32,767. So we can rearrange this to give us 2 to the power of n is equal to 32,768. And again, I'm going to solve this using not log to the base 2, even though that would work in this case. I am going to solve it using log to the base 10. So I can say log of 2 to the n equals log of 32,768. We can apply our log rule to rewrite this as n log 2 equals log of 32,768, and then divide both sides by log 2 to find the value of n. And this gives us n is equal to 15. So there are 15 terms in this finite sequence. So, having explored finite geometric series, we're going to now have a think about infinite geometric series and something we will later address, which is called the sum to infinity. So let's have a look at some examples of infinite geometric series. So here's my first example. It's 2, 4, 8, 16, 32. Now at the moment this is a sequence rather than a series, so it's a progression or a sequence as I'm not adding the terms together yet. Can you see it's divergent? And in this particular example, the R value is equal to 2. And that explains why it's a divergent sequence. You're doubling the values each time, so they're not going to approach a particular limit. They're going to get larger and larger. We'll have 64, 128, 256, so on. The terms will get bigger and bigger and bigger. Now here's another example of a geometric progression. 2, 1, a half, a quarter, an eighth. And I'll put a ... so it's an infinite sequence. And again, it's a sequence at the moment, not a series, because I haven't added the terms together yet. Now, you'll notice that this is a convergent geometric progression, and it converges to a limit of 0, i.e. the terms are approaching a term which is 0 effectively, because they're getting smaller and smaller and smaller each time. Now, the R value, in this case, is equal to a half. And of course, it makes sense that you then have a convergent geometric progression, because if you're halving the values each time, they will get smaller and smaller and smaller, which will result in the sequence converging. So this raises a question. When does a geometric progression converge, and when is it divergent? And what causes the convergence? And hopefully you can see that it is all related to the value of R. Now, if the R value lies between -1 and 1, then you will have a convergent progression. Now, having now learnt about the modulus function, there is a neat way of writing if R is between -1 and 1. You can say if mod R is less than 1, then your geometric progression will converge. So let's have a look at another example. What would happen if R was equal to negative a half? Well, let's imagine my first term is equal to 8. So my second term will be 8 multiplied by negative a half, which is negative 4. My next term will be negative 4 multiplied by negative a half, which is 2. And I keep multiplying by negative a half, and you can see my sequence is as follows. Now, what you'll notice is that the sequence terms oscillate. So they oscillate between negative and positive, but they converge to 0. We're now going to have a look at something very interesting, which is the sum to infinity of a geometric progression that converges. Now, this is something that only exists if your geometric series is convergent. So, for instance, if we have a geometric sequence, which is 2, 4, 8, 16, 32, and we convert it to a series by adding the terms together, you can see as you add in more and more terms, the sum will just get larger and larger. So nothing very interesting happens here. But if we have a convergent geometric progression, something more interesting happens. So let's take the geometric progression, which is 2, 1, a half, a quarter, an eighth. Let's make it infinite, so plus ... And let's make it a series, so we add the terms together. Now, if we just add together the first two terms, we get 3. If we add together the first 3 terms, we get 3.5. If we add together the first 4 terms, we get 3.75. And if we now add together the first 5 terms, we get 3.875. Now, what you'll notice is that something quite different is happening here to the previous example. Because the amount we're adding on each time becomes smaller and smaller and smaller, the sum of the terms is also converging to a limit. So they'll get to a point where you can keep adding values, but the values are so small that all that will happen is that you creep infinitesimally closer to a particular limit for the sum. Let's explore this in a little bit more detail on an Excel spreadsheet. So here we have this same sequence generated on a spreadsheet. So here we can see that these are the terms. And hopefully you can see that although I didn't use the notation in Excel, this stands for A1, A2, etc. So you can see all of the terms. Now, on the right-hand side, we've got the sums. So where it says S1 here, this is just equal to A1. But where we have S2 underneath, this is equal to A1 plus A2. And below that, where we have S3, this is equal to A1 plus A2 plus A3. So, for instance, when we get down to the very end here, S25, this is equal to A1 plus all the terms up to and including the 25th term here. Now, can you see what's happening to the sum? Hopefully, you'll notice that as we add more and more terms in, the terms that we're adding become smaller and smaller. So, for instance, by the time we add the 25th term, look at the size of the 25th term. It's so small, it's practically 0. So you keep adding on values which are absolutely tiny, which means you get to a point where the sum doesn't really change very much and it's starting to approach a particular value. Now you can hopefully see from the spreadsheet what that value is, and if I'd actually carried on with many more rows, Excel wouldn't really have been able to cope with the rounding very well. It would have rounded the value up to the sum. So can you see that as we add in more and more terms, the sum is approaching a maximum limit of 4. So that is what we call the sum to infinity. The idea being that even though if we add a finite number of terms together, we will never get exactly to 4, in theory, if we were able to add infinitely many terms together, this would give us a total of 4. Now, the concept of infinity only really exists in theoretical maths because you can't sit there and add together infinitely many terms. We've added 25 terms together and we have got very, very close to 4. The way to get to 4 would be to add infinitely many terms together, and we would write down that S infinity equals 4, and that is what we call the sum to infinity. Now, the sum to infinity only exists when you have a convergent geometric progression, because when you have a convergent geometric progression, the terms all start to approach a particular value. So you can see here the terms are starting to approach 0, and because of that you're adding on smaller and smaller amounts each time, which means that the sum will eventually approach a particular value. In this case it's equal to 4. Different geometric progressions, which have different a values and different r values, if they converge, will converge to different values of S infinity. So now our aim is to see whether or not we can find the sum to infinity of a convergent geometric progression as a formula. So let's consider the formula for the finite sum of n terms of a GP. Now, this is the formula that we found previously. It's S, and it's equal to A 1 minus r to the n over 1 minus r. Now, we sometimes write Sn here to indicate that we're adding together n terms, i.e. it's a finite sum. Now, what we're going to do is we're going to allow n to approach infinity. So we're basically saying, well, let's add together as many terms as possible. Let's let n get bigger and bigger and bigger. So we're going to add not just 25 terms together, we're going to add 1,000,000 terms together. Theoretically, the idea being we add infinitely many terms together. So this gives us S infinity, which is the sum to infinity. Now, what's going to happen here when we allow n to approach infinity? Well, the interesting thing is what's going to happen to r to the power of n. Now, because we are looking at a convergent geometric progression, we know that r is between 1 and -1. So, as n approaches infinity, as n gets larger and larger, what's going to happen to r to the power of n? Test it out on your calculator if you want to. Take a number like 0.3 and raise it to the power of 1,000,000. What do you get? Your calculator is either going to show you 0 or a very small value that is very close to 0. So r to the n will approach 0. So as we're working this through, we can effectively discount r to the n because it will approach 0, which means in the numerator we just have a multiplied by 1. So the numerator just becomes a, and the denominator becomes 1 minus r. Well, it is 1 minus r. And this is an extremely important formula. It allows us to calculate the sum to infinity for a geometric progression. Now, this sum to infinity only exists if the geometric progression converges, i.e., if r is between 1 and -1. It will not exist otherwise. So let's see whether this works with the previous example that we were looking at on the spreadsheet. Now that example started with a 2, and we then added on 1, we then added on a half, a quarter, an eighth, and so on. And this was our infinite sum. So you can see, hopefully, that a is equal to 2, r is equal to a half. Well, what about the sum to infinity? That's equal to a over 1 minus r. Now, we know in advance what we're hoping this will be because the spreadsheet indicated that as you add more and more terms together, you get closer and closer to a value of 4. But let's check. So this is equal to a, which is 2, divided by 1, take away a half, which is 2 divided by a half, which is equal to 4. So this confirms what we had already suspected from the spreadsheet. Let's have a look at a slightly different infinite geometric series. So 6 plus 2 plus 2/3 plus 2/9. So we can see that the first term in this series is 6 and the common ratio is 1/3. Now, if we're looking at the sum to infinity, always check your common ratio, and you can see that this is between 1 and -1. So the sequence will converge, which means that the sum to infinity does actually exist. So S infinity is equal to a over 1 minus r, which is equal to 6 over 1 take away 1/3, which is equal to 6 divided by 2/3, which gives us a value of 9. So the terms here will, as you add more and more of them together, the sum will become closer and closer to a value of 9. And again, if you want to check that on your calculator, you can set it up to do so, or on a spreadsheet, and you'll see that convergence. Let's have a look at a more complex example. An infinite geometric sequence has as its first 3 terms 9, 6, and 4. So our first job is to find the value of the common ratio. So we can just divide one term by the previous term to find out what the multiplier or the common ratio would be. So the common ratio would be 6 divided by 9, which is equal to 2/3. You can also check that, of course, by working out 4 divided by 6, which is also 2/3. So part 2, first of all, which is the first term in the sequence to have a value less than 0.5. So we're saying that some term must have a value which is less than 0.5, so ak is less than 0.5. Now let's remember that ak, the general term, is equal to a multiplied by r to the power of k minus 1. So a r to the k minus 1 is less than 0.5. Now what's a? A is equal to 9. So 9 multiplied by r to the k minus 1 is less than 0.5. Divide both sides by 9, which gives us r to the power of k minus 1 is less than 0.05 recurring. Now, this is what I was referring to earlier on. You can cause all sorts of issues if you try and use different bases here. Now we know that r is equal to 2/3, so I can say that 2/3 to the power of k minus 1 is less than this value on the right hand side. I am going to use either log to the base 10 or ln to solve this problem, and because it's an inequality, both methods will work. They always work. If I try and use some sort of other base like 2/3, you may find you don't get the correct answer at the end of this, or your inequality will not work. You have to be very, very careful when dealing with inequalities. So stick to using log to the base 10 or log to the base e, i.e. ln. So log to the base 10 of both sides. And I'm going to use my logarithm rule to move this power out to the front. So I get k minus 1 log of 2/3 is less than log of 0.05 recurring. Now, here's where you need to be very, very careful. If you work out the value of log of 2/3 on your calculator, you will find out that this is equal to negative 0.176. Now, you are dealing with an inequality. When you divide or multiply across an inequality by a negative number, the inequality sign has to reverse. So as you divide by log of 2/3, you will then get k minus 1 is greater than the result on the right hand side, which is log of 0.05 recurring over log of 2/3. Be very careful about this. You've seen this before when you were solving problems involving the binomial distribution, and you ended up with exponential equations which had to be solved very carefully with logarithms. Now this then gives us k is greater than, you can work this out by adding 1 to both sides, 8.1285 ... Now remember that k refers to a number of terms. It must be an integer value, and k has got to be bigger than 8.12, so you've got to round k up, and k equals 9. So which is the first term in the sequence to have a value less than 0.5? It's A9, or the 9th term. So now let's look at part 3. The terms in the sequence are added together to create a series. After how many terms will the sum be greater than 25? So we want to know when Sn, the sum of n terms, is greater than 25. So remember our formula for the sum of n terms. It's a 1 minus r to the n over 1 minus r. So we are saying that we want a 1 minus r to the n over 1 minus r to be greater than 25. Let's sub in our values. So a is equal to 9. So we have 9 bracket 1 minus 2/3 to the power of n over 1 minus 2/3 to be greater than 25. So again, let's be very careful as we deal with this, because this is an inequality. So you really, really need to be a little bit more careful than you would normally. Now, dividing by 9 is fine, because 9 is positive. So this gives me 1 minus 2/3 to the power of n, all over a third, is greater than 25 over 9. And then we can multiply it by a third, which gives us 1 take away 2/3 to the power of n, is greater than 25 over 27. Now, let's rearrange this inequality. So I am going to subtract 1. There are lots of different ways of doing this rearrangement, by the way. So that gives me negative 2/3 to the power of n is greater than negative 2 over 27. And I want to multiply both sides of my inequality by negative 1. Now, let's move the working up over here. So let's multiply both sides by negative 1, which of course gives me 2/3 to the power of n is less than 2 over 27. So remember, you multiply by a negative, reverse the inequality symbol. Make sure you've made a careful note about that in your notes as you go along with this. So now let's take logs of both sides. Now again, this is a situation where I completely urge you to make sure you use log to the base 10 or ln. Don't try and use other logarithms. With an inequality, you could find yourself making errors very quickly. So log to the base 10 of 2/3 to the n is less than log to the base 10 of 2 over 27. Log rules allow us to say that n multiplied by log of 2/3 is less than log of 2 over 27. And we're then going to divide by this log of 2/3. Now again, log of 2/3 is less than 0. It's a negative number, which means that you need to reverse the inequality sign. So n must be greater than log of 2 over 27 divided by log of 2/3. So n must be greater than 6.4190. So n must equal 7. So after how many terms will the sum be greater than 25? Well, the answer to that is after 7 terms are added together. Now, please go back and make sure in your notes you've made a very, very clear note here as to why the inequality sign was reversed. I'm going to write it down. Please make sure you do the same as well. So we reverse the inequality sign as log of 2/3 is negative. Now, log of a value that is smaller than 1 will give you a negative result. So whenever you are dividing or multiplying by a logarithm of a number, check whether or not it's negative or positive if you're dealing with an inequality. If you're dealing with an equation, life is a lot easier. If you're dealing with an inequality, you need to be extremely careful. So make sure you're using log to the base 10 or ln, and make sure that you check whether or not you need to reverse the inequality sign. So just a summary of those last 2 key points there. Be very careful when you're solving equations and inequalities using logarithms. Use log or ln rather than other bases. And if you multiply or divide across an inequality by a negative number, you must reverse the inequality symbol. And be very careful because log of x will be negative if x is less than 1.